Heat conduction is how thermal energy moves through a solid, flowing from a hot region toward a cold one. It is happening all around us, in a furnace wall, a heat exchanger tube, a frying pan, and the insulation in our homes. The question an engineer asks is simple. How fast does the heat flow, and what controls it? Fourier's law gives the answer. Picture a flat wall of thickness L with heat passing straight through it. Hold the left face hot at temperature T1 and the right face cold at the lower temperature T2. Because one side is hotter, energy flows steadily through the wall from hot to cold. Now plot the temperature against position as we move across the wall. At steady state, with constant conductivity, the temperature falls in a straight line from T1 to T2. The slope of that line is the temperature gradient, the change in temperature over a small change in distance. Fourier's law states that the heat flow is proportional to this gradient and to the area it crosses. Written fully, the heat rate Q equals minus K times the area A times the gradient dt over dx. The minus sign just means heat always flows in the direction of falling temperature. E constant K is the thermal conductivity, a property of the material itself. Copper has a high K, so heat races through it. Foam insulation has a low K, so it holds heat back. For a flat wall, the law simplifies neatly. 2K times A times T1 minus T2, divided by the thickness L. Try a brick wall. Conductivity near 0.7. Area 1 square meter. Thickness 0.2 meters. With a 100-degree difference across it, the heat flow works out to about 350 watts. We can read this just like Ohm's law for electricity. The temperature difference is a driving force, and the term L over Ka behaves as a thermal resistance. A thicker wall, or a lower conductivity, raises the resistance and less heat gets through. Engineers use Fourier's law to size furnace walls, choose insulation, and rate heat exchangers. And it is a foundation for every more complex conduction problem in 2 and 3 dimensions. One simple law, linking a temperature difference to the steady flow of heat.